All right, let me just point out a couple of things here. Okay, first is as we're getting closer towards AP exams, we're doing a lot of review, just with the packet that you're working on. But I want to make sure that you guys have additional resources if you want to do a little bit more than what we're doing in class, just for practice purposes. So on the spring review page at the very top, I put so here's a fall and spring summary sheets. I printed these out for you a couple weeks ago, so you guys should have those. But if you lost it, you can always print them out on your own. Here, there's also College Board has released FRQs for the past so many years, but I think 2000 2018 are probably the more recent ones. Oh, actually, it goes all the way to 2021. But if you click on that, you're going to see all the FRQs and the full set of solutions. If you click on scoring guidelines, it'll show you not only the key, but also show you the points, how they're grading it, and the point totals. Some are more detailed than others, but if you look, but most of them look more like this, where you got scoring guidelines, and then you have point totals. Every FRQ is worth 9 points, and kind of shows you how they're grading each of the FRQs. Some of the earlier ones have the problem above and then the scoring guidelines below. So that's nice to be able to just see the problem and the keys next to each other. There's also this link here. This is the AP Calculus Free Response Notebook. It's a collection of 1990 to 2010 AB FRQs, and it's organized by topic and category. So if you click on this, okay. While that's loading, let me point out a couple of things here. At the top, a couple of links are all FRQs, but the bottom here, we're dealing with multiple choice, and if you want to kind of get the feeling for what a full multiple choice experience looks like, these are multiple choice tests that's been released from College Board. That has all the multiple choice questions, and I included all the solutions as well. So there's always two parts. Part one is always non-calculator, and part two is calculator. So if you want to click through that and work through it or look through it, I think those could be very good resources for you if you choose to do anything beyond what we do in the classroom. And then College Board AP Classroom has a lot of practice problems, videos, and tips. So check that out. I've unlocked all the practice quizzes and tests. So if you want to go through and work through them, that could be beneficial as well. So this is what the notebook, Free Response Notebook looks like. If you click on, go to table of content, right? All the related rates, FRQs are grouped together, all the derivative graphs, FRQs are grouped together, all the area volume FRQs are grouped together. So that's nice to, if you want to just look through particular FRQs, you can do that. So that's resource there for you. Okay, so I'll make sure that you guys knew about that. Okay, so what I have printed out for you here's an exhaustive list of derivative and integral rules. Now on page, the last 2 pages of your packet, I have multiple choice summary sheet, and those I put, I grouped together all the most common derivative and integral rules. So if you want to memorize just the bare minimum, look at the last 2 pages of your multiple choice packet. And I think it'll be good if you at least look through that. But if you want to get the full derivative list and integral list, they're here. Okay, from Powell rule all the way to our trig. Rules 25 to 36 are not for our course, so we can cross those out. And the bottom half are all the integral rules. For some reason, they left off Powell rule and natural log rule, so I put them down there as 19 and 20. Right, but all these rules we use and could show up potentially on the AP exams. And then I have this other sheet that may be also good for you to have in terms of if you want to just once you feel like you have a good feel for all the derivative and integral rules, here's a chance for you to practice and write them down, see how much you know, and then I have the key on the back that you can check. Okay. I'll also put these links up on the website. I'll put it near the top of the spring review page. So if you want to print extra copies of this out for yourself as you go through and practice, you're welcome to do that. Okay. So again, guys, formulas are not going to be provided for you on the AP exam. The most they'll give you is maybe volume of a sphere or volume of a cone. They may give you geometric formulas, but they're not going to give you any calculus formulas. Okay, we have to know them. The good news is that there's a significant curve on the AP exam, and second is that typically they tend not to focus on the more obscure rules, right? So the major rules are the ones that typically show up on the AP exam. But every now and then there's always going to be some of the more obscure rules, such as like a to the u. Sometimes that shows up on AP exams, or integral. Some of the more obscure integral trig rules sometimes show up, but that's usually few and far between. Okay, let's look in your packets, and I'd like to work through some problems on page 4. Okay, we got through derivative rules, we got through limits, we got through continuity, and the next big topic, this is from the end part of chapter 2, and that's implicit differentiation. So if you guys go to page 4, if you've done it already, great. But I'd like to still kind of go through each of the steps with you in detail and make sure you're comfortable with implicit differentiation. It's a big topic on the AP exam. Okay. And also to be able to recognize it, right? You're not going to see a problem where it says, oh, this is an implicit differentiation problem. Apply those rules. You have to be able to recognize those things. So this is page 4, number 18. Okay, does everybody have this packet? Okay, make sure. Okay, so how do we know that we're dealing with implicit differentiation here? We look at the variable here. We see that the variable y is not in its usual place. It's not y equals and everything else on the right. You see y kind of mixed in to the equation. And also, if there's multiple y's involved, you know, we got to do implicit. And what is implicit? Implicit is where we have to keep track of the y derivatives. And the way you keep track of y derivatives is we have to attach a dy dx as soon as we come across y's derivative. Okay, so so we go through power rule for sure, implicit for the y, but there's something else here. Can you identify something else that we have to involve here if we want to find the derivative? You guys see it? Yeah, this 4xy, it doesn't announce itself, but there's product rule here. 4x and y are complete separate terms. They're being multiplied. We can't merge them together, so we have to go through product rule. And there's something else where students make mistakes. Can you spot where that could be? Doesn't seem like a big deal, but it's a common place for students to potentially make a slight mistake and it throws off all their answer. Okay, product rule looks like this: f prime g plus fg prime. Yeah, that negative causes students a lot of trouble because if you just do product rule f prime g plus fg prime, and you don't remember that this negative is going to end up impacting the entire term, you got to distribute that negative through to the second term as well. So it's nice to remember that there's really a parentheses there. When you go through product rule, that negative has to distribute to both terms. So that's something that we have to be careful about. Okay, so let's go through implicit here. Okay, 3x squared becomes 6x. That's the derivative. We don't do anything special with x's. With x's, we just find the derivative and like the same way that we did in the past. Okay, I'm going to set this up here, minus parentheses. We got to go through a product rule. I'm going to set things up here, f prime g plus fg prime. Okay, we'll fill that in later. What does 1 become? 0. Okay, let's go through our derivative rules here. So f prime g, 4x becomes 4. G stays as y. Back to f. And then g prime. So y's derivative is what? Yeah, 1 dy dx. Yeah. Okay, let's see how much we can clean up, solve for dy dx, and then we can figure out what else is asked of us. Okay, careful here. Now that parentheses is helpful, right? Reminds us to distribute the negative through. Okay, divide both sides by negative 4x. All right, so going back to our problem, it's not only asking for dy dx, it's asking for the derivative at a point. So I see that if I plug in 1 for x, I'm still missing y. So I want to get it all the way down to a number, but I'm missing the y value. Okay, so how can I find the y value? Is there anything available to us that can help us find the y value? Because we can't just leave our answer as, you know, plugging in 1, sorry. Okay, into what? Good, yeah, original, right? So the original equation will help us get to any order pairs that we're looking for, right? So we can insert 1 into the original equation, and then we can find the y that we need for our derivative. Okay, subtract 3 from both sides. Divide both sides by -4. I get y equals 1/2. Okay, so replace x and y. Now I have my x and y value. This is usually the notation that we use to indicate that we want to insert both the x and y value into the derivative. We use the vertical bar with order pair next to it, and now we can replace every x and y with 1 and 1/2. Okay, 4/2 is 2. 2 minus 6 is -4. -4 over -4 is 1. So the slope of my curve at this order pair is 1. Answer choice B. Okay, I'd like to do another implicit problem with you. So let's look at number 19, very bottom of page 4. Nineteen says, find the slope at 3, 2. Same idea here. Okay, so we should be able to look at an equation and be able to understand that there's implicit involved because we see y's kind of all over the place. It's kind of it's not like a function, right? It's just not like y equals and everything else, all the x's on the right. Whenever you see y's mixed into the equation, that's an indication we got to keep track of our dy dx's and do implicit. Okay, so same process here, right? You got power rule. And do you see this 2xy here? We also need what here, 2xy? Right, that's also product rule, right? And then you got to make sure you distribute that negative through as well. So this would be the same method involved here between 18 and 19. Product rule and distributing the negative through. Okay, so let's go through. First few terms is just power rule though. But we see y here, so as soon as we find the derivative, we got to attach a dy dx. Nothing special for the x's. 6 goes away to 0. Protect the 2xy with a set of parentheses. The negative has to distribute through. Here's my f, here's my q. Okay. F prime g plus fg prime. 2x becomes 2. Y stays. F stays as 2x. And then what does y become? dy dx. Yes. Okay, so now it's just a matter of cleaning up. Try to distribute the negative through, merge all the terms together, like terms, or not like terms, but we can group the dy dx terms together, factor that out, solve for dy dx, and then finally insert our order pair 3, 2. Distribute the negative through, and then our next step is to try to group all the dy dx terms together. So let's put all the dy dx terms on the left side and everything that does not have dy dx, move them to the right. factor dy dx out, and then divide the parentheses over to the left side, sorry, to the right side. Order pair 3, 2, we can now involve that with our derivative. dy dx, vertical line, order pair 3, 2. And insert and find your slope values. Okay, any questions? So that's implicit differentiation. Next up, we're going to do related rates. Related rates kind of has a similar feel to implicit. It's just that instead of dy dx, we're dealing with a different independent variable. It's a variable that we don't, it's not in the problem, but it's within the description. It doesn't show up as a variable, but because time is now going to be the independent variable, everything is going to have a d over dt. So instead of, so imagine this is a problem with involving related rates, then this will become 6y dy dt. This will become 4x dx dt, and then you have dx dt and dy dt. So instead of d over dx, everything's over dt. Okay, so let's look at some of these related rates problem. This is on page 5 of your packet. Okay, so right now I'm kind of giving these headers to indicate the topics that we're on, but on the quiz, the problems will be kind of mixed. Okay, same as your AP exam. Your AP exam is not going to organize it, you know, saying, hey, this limits problem. Okay, now we're moving on to derivatives, and now we're on the related rates. All the multiple choice will be mixed. Okay. All right, the way that we know this is a related rates problem, let me read the problem first. The radius of a circle is decreasing at a constant rate of 0.1 centimeters per second. In terms of circumference, what is the rate of change of the area of the circle in square meters per second? So if it doesn't announce related rates, which you're not going to see it, is you're looking for anything involving time. Anything involving time is an indication that, okay, this is going to be a related rates problem. There's time involved, okay, and there's going to be d over dt I got to worry about. So we know we're dealing with two equations here. We're dealing with circumference, we're dealing with area of a circle. So let's go ahead and write those formulas out. Area is pi r squared. Circumference is 2 pi r. Okay, it's best if we memorize these formulas. I've seen AP exams where sometimes they provide it and sometimes they don't. So I think these are very common ones that we need to know. Oh, here's something I think is helpful. If you know that a equals pi r squared, but then you forget what the circumference formula is, look at it from this perspective. What's the derivative of pi r squared? 2 pi r. Okay, so there's that derivative relationship here. So if you somehow forget the circumference formula, but you still remember the fact that it's a derivative, if you know the area formula, you can work your way to the circumference, just the derivative of each other. Okay, let's go ahead and find each of the derivatives. We know that we have dA dt, dc dt potentially involved. We may not need everything that we're finding, but better to have more than not enough. Okay, so let's find the derivative here. A becomes dA dt. Okay, what does pi r squared become? 2 pi r, but what else is needed? dr dt, right? Time is impacting every variable. Remember, pi is not a variable. Okay, pi is just a coefficient. Okay, we may or may not need this. Let's go ahead and find the derivative anyways, just so that we have it. What does c become? dc dt. Okay. C becomes 1. We attach dc dt. What does 2 pi r become? 2 pi. The r goes away, but we're asking for r's derivative, so we need to attach dr dt. Okay, so. All right, let's gather some information from what's provided. The radius of a circle is decreasing at a constant rate of 0.1 centimeters per second. Okay, what can we assign that 0.1 to? Which variable is that talking about? Okay, dr dt. Any adjustment we have to make there? Negative because why? Decreasing, yeah, decreasing. In terms of circumference, C, what is the rate of change of the area of a circle? Okay, what are we looking for? dAdt. That's the unknown. And if this doesn't make sense in terms, it says in terms of circumference C, like what does that mean? If you look at your answer choices, you can kind of understand why, right? So we want to find a way to involve C into our into dAdt that we're looking for. Okay, so we're trying to find dAdt. Do you see a way that we can work in the variable C into our answer? Yeah, substitute. What substitution can we make? Good. So C can replace 2 pi r because we know that C is 2 pi r, right? So we can make that substitution to make it look like our answer choice. And then we can also replace dr dt with, yeah, negative 0.1, and that should move us towards hopefully matching one of our answer choices. Dr dt. Okay. Question so far? Okay, let's look at number 2. The radius of a circle is increasing. At a certain instant, the rate of increase of the area of a circle is numerically equal to the rate of increase in the circumference. What is the radius of the circle at that instant? So we're still dealing with area, circumference. So I think a lot of what we found from above can carry over to number 2. So let's see if we can get this second long sentence into something that is more equation form here. Okay, let's break this down piece by piece here. Rate of increase in the area of a circle. What is that referring to? dAdt, okay. Is numerically equal. So if I see the word is equal to, I know I'm looking for an equal sign. So I do that. Is equal to twice the rate of increase in the circumference. Okay, how can I replace that with that phrase with something formula-wise? Say it again. Good. So twice, that's 2 times dc dt, rate of increase in circumference. Okay, so something that's more useful to me now. Okay, what is the radius of the circle at that instant? Okay, well, we have dAdt here and here, so why don't we make that substitution? Okay, so let's start off with the fact that I've already gathered information about the dAdt, which is 2 pi r. I'm trying to find the radius, so ultimately I want to get this r by itself. And it's just going to feel like a puzzle now. How can we make substitutions and clean things up and try to get that R by itself, get it down to make it match one of our answer choices. Okay, so I can replace dA dt with what? What's another? What did we gather here? dA dt. Thank you. Good, right? We have that substitution that we can make, so let's do that. All right, I have two different versions of dA dt. Maybe I can set them equal to each other. Okay, we still have too many variables here, right? I still got dc dt, I still got dr dt, I still have r. I want to solve for r, but I want r in terms of a number, not in terms of variables. So is there any other substitutions that we can potentially make? Right, so we have this, right? We have another version of dc dt. We know c is 2 pi r, so dc dt is also 2 pi dr dt. So I'm going to make that substitution here. This dc dt can be replaced with this piece here. All right, let's see if that leads us to anything here. 2 times dc dt is 2 pi dr dt here. All right, so do you see a way for us to get that r down to a number here? What can I do with these remaining drdts? Yeah, divide them out. They'll just cancel and go away, right? Okay, so now the only variable left is r. Remember, pi is not a variable here. We can just divide that 2 pi over to the left side. 4 pi divided by 2 pi is r. Now we can get it down to a number. Okay, number 3. If the base of a triangle is increasing at a rate of 3 inches per minute, while its height is decreasing at a rate of 3 inches per minute, which of the following must be true about the area of the triangle? Okay. Let's go ahead and build the area of a triangle first. What's the area of a triangle? Yeah, 1/2 base times height, okay. Okay, we know this is related rates because we see base increasing with respect to time, height increasing with respect to time. And it says which is true about the area. We're talking about area that's increasing, decreasing. So we know this is dA dt. So we have to deal with dA dt, dB dt, dH dt. We're going to have to find the derivative. Time is going to be our independent variable. Related rates going on here. So let's go ahead and see if we can find the derivative so we have something to kind of build off of. A becomes dA dt. Okay. What can I do on the right side? Can I just say, okay, I need both variables, so I can make this dB dt times dH dt. Can I do that? Gotta do product rule. I know it's easier to just say dB dt times dH dt and be done with it, but that's not the correct form. Now, if it was b plus h, then we can say dB dt plus dH dt, but anytime we have variables multiplied together, we're forced to have to go through product rule. Okay, so product rule here. Okay, f prime, what's 1/2 b's derivative? One half, and b turns into what? Okay, related rates, so what do we need? B dt, right? Every variable is going to get impacted by time, so dB dt times h, back to f, g prime, okay, what's h's derivative? Okay, so that's our anchor. That's what we're going to be building off of here. Okay, now let's go back to our problem. Let's see if we can assign some values to variables here. Base of a triangle is increasing at a rate of 3 inches per minute. Right? What can we do with that first sentence? Get positive or negative? Because increasing. Okay, so dB dt is positive 3. Okay, height is decreasing at a rate of 3 inches per minute. What can we do with that information? The HCT is -3. Okay, so let's plug it in and see if we can make it down to a simpler equation that we can begin to maybe make the correct conclusion. dt is 3. Okay, let me clean this up here. dA dt. 3/2 h minus 3/2 b. Okay. Maybe it's helpful to factor 3 out. Let's just have different variations, and we can see if which makes sense. All right. We don't know what h and b are. Okay. H and b could be anything, but we want to be able to make the appropriate conclusion here. A is always increasing. That's saying, is dA dt always positive no matter what h and b are? Okay. Not always increasing, right? I can force a negative into this situation if I just made b the larger value. Right, so I'm not always going to get a positive dA dt. It depends if whether h is larger or whether b is larger, right? So we know we can eliminate first choice. A is always decreasing. True or false? False, right? Again, I can force h to be larger, and all of a sudden dA dt is positive, and that's going to go against with that second statement. Okay. A is decreasing only when b is less than h. False, right? Imagine b is smaller than h, then this is going to end up being a positive value. Let's say it's 4 minus 1 or 6 minus 3. So that's not true. A is decreasing only when b is greater than h. That's true, right? If b is greater than h, then I can guarantee this will give me a negative value, and negative dA dt would mean A is decreasing. Let me ask you this. For E, it says A remains constant. What is that saying? That means it's saying that dA dt must be what? Okay. But A remains constant means the derivative is 0. Okay. So, but we know that's not true, right? dA dt is only going to be 0 if h and b are the same, but we can't guarantee h and b are the same. So dA dt is not guaranteed to be 0. Not always. Okay, good. Try number 4. Number 4, I feel like it's more straightforward. You have your equation. List out your information, find the derivative, and then just make your substitutions. Okay, so try number 4. Okay, start with s equals 4 pi r squared. Find your derivative. Your d over dt will start popping up for each of the variables. Okay, s becomes ds dt, 4 pi r squared becomes 8 pi r dr dt. Gather information from the problem. Dr dt is -2, right? The radius is decreasing at a rate. We know that it's talking not about a static value, but a changing value. So dr dt is -2. Radius is 3. And we're looking for ds dt. We're looking for the rate of change of the surface area of the sphere. Okay. Once you gather information, then it becomes easier. Just substitute and get it down to a numeric value. Okay, any questions here? Another important topic within related rates is dealing with similar triangles. So similar triangles can come in 2 forms. Usually it's cones or these shadow problems. So these shadow problems tend to be a little bit easier, but it also requires us to kind of know the how to set it up and kind of like the defining variables, the values of, or how to define some of these variables that show up. Okay, so let's walk through this problem here. Page 6. Okay, so these shadow problems are always going to kind of be set up this way. Okay, we're trying to force a triangle inside a triangle here. So you see a triangle inside a triangle. Let me just put it to the side here. So it feels more geometric. So we see there's a triangle within a triangle here, right? Let me highlight with markers here. So inside triangle, orange. And then you got the big triangle I have in yellow. All right, we set everything up. Usually the heights are provided. Okay, person is 6 feet tall. Height of the street light is 15. And we typically have X and Y. That's the base. That's how I do it. Okay. All right, so we're going to set proportions here. We'll say height of the small is to the height of the large as base of the small is to the base of the large. Okay, so we'll start with the heights. Height of the small triangle is to the height of the large triangle as the base of the small triangle. So what's the base of the small triangle represented by? Good, y, right? Not x. I know x comes first, but you see x is not the full base of a triangle. Y is. At least the way that I defined it. Divided by the base of the large triangle. What can I do to represent the base of the large triangle? Is it xy? There's the x plus, yeah, x plus y. So careful, right? I know we wanted to say x times y, but x times y is not going to be the length of this base, is x plus y. So x plus. Okay. We're going to get everything cleaned up, and then we can bring in the time aspect of it, where we do d over dt. Okay, we'll cross multiply here. Let's combine some like terms. Subtract 6y from both sides. All right, so now we have a relatively easy equation here. Let's go ahead and find the derivative. Remember, time is our independent variable. What does 6x become? Yeah, 6 dx dt. And what does 9y become? 9 dy dt, okay. Now, to move forward with this problem, I want to be able to make sure that we understand what each of these mean, right? So here's something that you can write down. dx dt means the rate at which the person is walking either towards or away from the lamppost. dy dt is going to be the rate of change of the length of the shadow. Okay, it's just going to be the rate of change of the length of the shadow caused by the person moving. But then if I add the two rates together, I end up with the rate of change of the tip of the shadow. Okay, so let's gather some information here. We already have the 6 feet. We have the 15 feet from for our diagram. It says the person is walking along the path at a rate of 4 feet per second. So what can we assign that 4 to? What do you think? Person is walking away from the base of the street light at a rate of 4 feet per second. dx dt, okay? Positive or negative? Positive because getting bigger, good. Walking away, which is cause that x value to grow. So we know dx dt is positive. Okay. What is the rate at which the person's shadow is lengthening? What are we ultimately looking for? Which variable? Just dy dt, right? Shadow lengthening is just dy dt. Plug in, solve, and we get that 2.667. Okay, I'll check pages 5 through 8 tomorrow. But I'll probably go through a lot of those problems from page 5 through 8. Still want to go through curve sketching, and then if we have time, we may either start reviewing for the. But I think we'll probably go ahead and start with second semester material if we're done with that tomorrow. Okay. Again, our quiz is split into 2 days, next Wednesday and next Thursday.